This experiment studies the absorption of oxygen from air into the oxygenated water using a falling film absorber. The objective is to evaluate gas-liquid mass transfer performance and determine the relationship between Sherwood number and Reynolds number using the correlation. So as you can see, the correlation inside the slide. SH equals to ARE to the power of M. The oxygenated water flows downward as a thin film while air flows upward in a counter-current contact. Dissolved oxygen at the inlet and outlet is measured to determine molar flux and liquid phase mass transfer coefficient. So right here on the right, we have Henry's law, which is the concentration equals to Hp. Henry's law is applied to estimate the equilibrium concentration at the gas-liquid interface. Sherwood number, Reynolds number, and SC are calculated to characterize mass transfer behavior. A log-log plot of SH and R versus RE is used to determine the empirical constants A and M. Results provide insight into gas-liquid mass transfer and the industrial applications of falling film absorbers. Introduction. Gas absorption is the transfer of a gas from the gas phase into a liquid phase. A falling film absorber is a gas-liquid contactor where where liquid flows downward as a thin film and gas flows upward in the countercurrent direction. The efficiency of absorption depends on flow rate, fluid properties, and also the mass transfer coefficient itself. Common industrial applications that we can find nowadays are in gas purification, carbon dioxide removal, and also oxygen absorption processes. So for the experimental overview, oxygen from air was absorbed into the oxygenated water. Water was deoxygenated using nitrogen purging. Air entered from the bottom while water flowed from the top of the column. Dissolved oxygen (DO) concentrations at the inlet and outlet were measured at steady state. Experimental data were used to determine the liquid side mass transfer coefficient and also to develop the Sherwood-Reynolds correlation. This is the objective. So the objective of this experiment, which is the falling film absorption, is first to study the absorption of oxygen from air into deoxygenated water in the falling film absorber. The second, to determine the liquid side mass transfer coefficient (KL) based on experiment measurements. And third, to calculate the Sherwood number and Reynolds number for different operating conditions. And lastly, to establish the power law relationship between Sherwood number and Reynolds number and compare the obtained correlation with values reported in the literature.
Okay, now I will talk about methodology for our experiment 6. The experiment was carried out using a falling film absorption apparatus to study the absorption of oxygen from air into the oxygenated water. Water in the sump tank was first deoxygenated by purging with nitrogen gas and circulated through the system until stable dissolved oxygen (DO) readings were obtained. The oxygenated water was then introduced at the top of the absorption column, while air was supplied from the bottom at a constant flow rate of 5 liters per minute, creating a countercurrent flow arrangement. The water flow rate was adjusted to form a uniform liquid film along the column wall, and the system was allowed to reach steady-state condition. Next, for DO concentration, which is inlet and outlet recorded for different flow rate. Our data that used to calculate, which is oxygen molar flux, mass transfer coefficient, and Reynolds number, scheme number, and Sherwood number. Sherwood against Reynolds plot used to obtain empirical correlation. That's all from me.
Okay, so let's look at the result overview table on the left. As the water flow rate increased from 60 to 250 ml per minute, the molar flux of the oxygen increased from 2.44 times 10 to the power negative 6 to 2.27 times 10 to the power negative 5 mole per meter per second. At the same time, the liquid side mass transfer coefficient K also increased from 7.69 10 to power negative 6 to 7.15 times to power negative 10 to power negative 5. This shows that the increasing the water flow rate enhances oxygen absorption performance because higher flow rate improves mixing and reduces mass transfer resistance. Next, looking at the Reynolds number versus Sherwood number table on the right, we can see that um, the both Reynolds number and Sherwood number increasing water flow rate. The Reynolds number from 39.09 to 162.87, indicating a higher degree of turbulence in the system. Correspondingly, the Sherwood number increased from 129.50 to 1204.06. This relationship suggests that greater turbulence improves mass transfer efficiency, leading to better oxygen transfer between phases. Finally, the Sherwood number and the Reynolds number correlation, the experimental values obtained were A is equal to 0.213 and M is equal to 0.648, while the literature values are 0.67 and 1.2 respectively. Although there are differences between the experimental and literature values, the overall trend still follows the expected relationship between Sherwood number and Reynolds number. These deviations may be caused by experimental limitations, measurement errors, or assumptions made during calculation. In conclusion, the results confirm that um, increasing the water flow rate improves the turbulence, enhances mass transfer, and increases oxygen absorption efficiency.
And now moving to discussion. So increasing the water flow rate improved oxygen mass transfer and the falling film absorber, and higher flow rates increased turbulence and mixing, which reduced the thickness of the liquid film and lowered mass transfer resistance. During the deoxygenation process, the stronger turbulence also enhanced oxygen stripping by nitrogen gas, creating a large concentration gradient between sensor 1 and sensor 2. As a result, oxygen transfer became more efficient, leading to higher absorption performance and increased mass transfer efficiency. Now moving to other part of the discussion. So the experimental correlation between Sherwood number and Rayleigh number showed the same overall trend as the theoretical model, indicating that mass transfer increased with increasing flow rate. However, deviations were observed due to experimental limitations, such as incomplete deoxygenation, non-uniform wetting of the column, sensor stability, and fluctuations in flow rate. These factors affected the concentration measurements and contributed to differences between the experimental and theoretical results.
Okay, so now moving to the conclusion and recommendations part. So for conclusion, increasing the water flow rate enhanced tolerance and improved oxygen mass transfer efficiency. Higher Reynolds and Sherwood numbers indicated better mass transfer performance. The molar flux of oxygen increased with water flow rate, confirming improved absorption. Experimental results generally agreed with the theoretical trends, although deviations were observed due to non-ideal conditions and measurement limitations. And for the recommendations, increase nitrogen flow rate or contact time to achieve complete deoxygenation. Ensure uniform liquid distribution to maintain a stable falling film. Perform repeated experiments and investigate a wider range of flow rates to improve data reliability. Improve gas liquid contact area through better packing or surface design to enhance mass transfer efficiency. And that's it. Thank you, everyone.